Hey guys, it's Off1 here, and today we're going to be solving jump game. In this problem, we're given an integer array nums, and we're told that we're initially positioned at the array's first index. So, for example, we're going to have to always start at this first index, and they tell us that each element in the array represents the max jump length at that position. So, if we start at 2, that means we can either jump to this next index, or we can jump 2 indexes. And the problem wants to return true if we can reach the last index, or false otherwise. So for this example here, we only have to reach this 4. And we can see that if we start from this 3, because we already made it from 2, then we can make it to 4, because this would be 1, 2, and 3. So we return true here. For this example though, let's say we start at this first index, because we have to start there. We can jump to the next index, to this 1 here, or to the 0. And from here, we can go to the next index and see if we can reach the 4. But as you can see, we cannot. We end up at the 0 again. And same thing if we start at this 1, we can also only make it to 0. So because we can't reach this last index, we return false. So here I've written the example from the problem, and I've also put the indexes on top of the numbers so it's easier to understand what I'm doing. And now we're going to start. So we're always going to start at index 0, and the max jumps you can do here is 2. So let's write that down. Start at index 0, and we can either do 1 jump, or we can do 2 jumps. If we do 1 jump, we're going to end up at index 1, and at 1 we have a value of 3. So that means we can do up to 3 jumps. So we're going to have 1, 2, and 3, and now we see where we end up now. So if we do 1 jump, we end up at index 2. If we do 2 jumps, we end up at index 3, and if we do 3 jumps, we end up at index 4, which is what we want to do, but now let's just continue the tree to see what happens. So at index 2, we can only do 1 jump, and same thing for 3, we can only do 1 jump as well. So here we would end up at index 3, and here we end up at index 4. And same thing here, we can only do 1 jump, so we end up at 4. And now we go to this other part of the tree. If we do 2 jumps, we end up at index 2, and from index 2, we can only do 1 jump, and then that puts us at index 3, and then index 3, same thing. We can only do 1 jump, and that will take us to 4. So as you can see here, we're doing a lot of repeated work. For example, we went to this 3 multiple times, and instead of having a calculator each and every time to see if it gets us to the end, we can just store it in our DP array. And also same thing for 2 here. We went to it multiple times. To get rid of the repeated work, we could just store this in, for example, a DP at the index 2 and DP at index 3. So that way we know in the future that we already went there and don't need to recalculate it. But the problem is that this solution takes up something like O of n squared time, I believe, since we have to go through every single index, and then for every index we have to iterate this many times to be able to update our array. So for example, for 2 we would need to update index 1 and index 2, and for 3 we would do the same thing, update this index, and that index. And you can see that's a lot of work. There's actually a much simpler solution that is also more intuitive in my opinion. So what we're going to do is start by putting a pointer here at index 4, and we're going to start by looking at index 3. So can we get to 4 from index 3? Yes, because we can make 1 hop, and that would get us to 4. So now we can just move this pointer to the left one. So now we can see that we don't care if we can reach this last part, because now we only care if we can reach this number, since we have already verified that we could go to the last one. So now we check the previous index. So can we go from here to here? Well, yes, because we only have 1 hop available, but that's enough to get us to index 3. So now we move this pointer over here. And now we do the same thing. We don't care if we can reach this number anymore, because we already verified that we could. And now we check the previous index's number. So can we reach index 2 with this number? Well, yes, all we need is 1 hop. Now that we verified that, we can move the pointer to the left again. So now we do the same thing. We don't care if we can reach this number anymore. We only care about reaching this number. And if we check this index here, we see we have a 2, and we only need 1 hop to get there. So we can move this pointer to the left again. Now at this point, we're at index 0. So again, we don't care if we can reach this point, and we verified that we could reach every single point, so we could return true because our pointer is pointing to index 0. So again, if our pointer points to index 0, we return true. If it ended up over here, then we know we couldn't reach the beginning, which means there's no way to get to the end either, so we would return false over here. So our pseudocode could look something like this. So if the current index we're at plus the current number we're looking at is greater than or equal to the pointer, and this pointer is going to be an index, so just remember that, then we want to update our pointer to point to our current index. And then at the end, we return true if our pointer is 0. And that's basically it for our pseudocode. So as far as the time complexity goes, the time is going to be O of n because we're only iterating through the array once, and we're actually going to do it backwards in our code. So still O of n. And for space, we're only using a pointer variable here to keep track of where we're at, so it's constant space since we don't need a DP array. So now we can get into the code. To start, we're going to initialize our pointer variable, and it's going to be pointing to the very end of the nums array. So it's going to be length nums minus 1. And from here, we just want to iterate through our nums array. So for I in range of length of nums minus 1, and then we're iterating backwards, we want to do our check. So if I, the current index, plus the current number we're looking at is greater than or equal to our pointer, then we update our pointer to be our current index. And that's the whole code. After that, we just return if our pointer is equal to 0, then this is going to return true, otherwise it's going to be false. And now we can just submit the code. So as you can see, this code is pretty efficient, and now I'll go through the code manually. So to start, we want to initialize our pointer, and it's going to be at length of nums minus 1. So this would be 5 minus 1, which is equal to 4. And you can see that it's pointing to index 4. So that's checked off. And now we just do for I in range of length of nums backwards. And let's say we're starting here. Now we check. If I plus nums of I is greater than or equal to our pointer, then we update our pointer. So let's see. I is currently 3, and the current number at I is 1. So 3 plus 1 equals 4. So that does meet our condition. So now we just want to update our pointer to I. So now our pointer is pointing to 3, and we can do this condition again. I plus nums of I is greater than or equal to our pointer. So we're looking at index 2, and the index 2 number is 1. So 2 plus 1 does equal 3. So that's just barely enough to move our pointer. So now we update it again. And now we do this again. So I is currently 1 because we're looking at this index, and our nums at I is 3, and we can see that 1 plus 3 is greater than or equal to 2 because that's where our pointer is currently. So now we can move it to the left again. And now we're at our last iteration. So we're looking at this index here, and now we check 0 plus 2. That is greater than or equal to 1, so we're going to move our pointer to the left again. So now at the end here, we can see that our pointer is at 0, so we're going to return true here. And that's correct. If this video helped you in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.